In this video, we're going to look at a new helper function rule. It's called the operating on a list rule. And as you'll see, what it says is that if you're coding a function and you reach a point where you need to operate on a list, not just the first element of the list, but the whole list, or at least potentially the whole list, then you need a helper function to do that. Now I'm going to work on sort images. Let's see. Function operating on a list, we should do the base case first. So if we're going to sort images of an empty list, well, if it's already empty, there's not a lot to sort. It comes back empty. Now we need an example that's at least too long. And I've got some good examples up here in arrange images. So let me just grab this one. Go back down here to sort images. So let's see. Check, expect, sort images of this. Get rid of that extra space there. Now if I'm asked to sort a list that's already sorted, I better not unsort it. This list is already sorted, so there's no use retyping it. That's just an opportunity to make a mistake. And Command I fixes the indentation. And what does that say? That says if you get a list that's already in increasing order of size, then leave it in that order. And there's been this ambiguity floating around about what size means, and I'm going to clarify that size means area. Okay, so that's an example where they come in already in order. Let's make an example where they come in out of order. And we can just do that by swapping these two rectangles again. So now they come in with the big one first and the little one second, and we need to confirm that when we produce the list, they're in the other order. So that's pretty good for some examples. Save the file here. Now let's go get the template. We'll comment out the stub. We'll rename the template, rename the natural recursion. We'll start with the base case. That's usually the easiest, and this test tells me that the base case result should be empty, so that is easy. Now let's think about the recursion case. Sometimes the first element of the list goes right at the beginning of the rest of the list in the result. That's this case here. The first element of the consumed list goes at the beginning of the rest in the result. It sort of stays where it is. But sometimes the first thing in the list doesn't go at the beginning. And I guess if these lists were long, the first thing in the list could go somewhere. Let's make another example here. Let's make an example where the first thing in the list is 30, 40. The second thing in the list is 10, 20. And the third thing in the list is 20, 30. That's got to come back in the order 10, 20, 20, 30. Let me make this red so we don't get confused. And we'll make that one green. That's got to come back in the order 10, 20, 20, 30, and then that one. So this thing, which starts out first, ends up third. So this somehow has to go in the right place in the rest. But notice we don't have the rest. What we have is the result of the natural recursion. Now there's a really important point here for a function like sort. Remember, we're supposed to trust the natural recursion. And what trusting the natural recursion means is it means trusting that it's going to do its job. So that means that whatever comes back from the natural recursion will be what? Well, it'll be a list of image because the signature says list of image. But what else will it be? Well, it will also be sorted. The result of the natural recursion will be sorted. And so that means I'll have one image in my hand, and I'll have a sorted list in my hand. And what I need to do at that point is manage to stick the one image in the proper place in the sorted list. And what these examples are telling me is sometimes it'll go right at the beginning of the list, but sometimes it'll go farther down in the list. And in fact, because it's a list, the list could be arbitrarily long. And this first value that I need to stick into the result of the natural recursion could be going very far down the list. We just don't know. That's what arbitrary size means. So there's a helper function rule that says that if you need to operate on arbitrary size data, if you're at a place where all at once you have to do an operation on arbitrary size data, you have to use a function to do it. In fact, you have to use a recursive function to do it, because you don't know how far into the data you have to go as part of the operation. So that helper rule basically says right here, we need to call a new function, insert, and we're going to wish for it. Let's wish for it right away. It's going to consume an image, because first of LOI is an image. And it's going to consume a list of image, because the result of the natural recursion of sort images is a list of image. So it's going to consume an image and a list of image, and it's going to produce, well, it has to produce whatever sort images is supposed to produce, so it has to produce a list of image. And what does it do? Produce new list, comma, with image in proper place in list in increasing order of size. That's a little cumbersome. Let's see if I could say that better. Let's just say insert image in proper place in list in increasing order of size. And just to be clear about what I mean by image and list, I'll give names to the parameters right away. This is the stub, and the stub has to produce some list of image, so it'll produce that. So insert image in proper place in list in increasing order of size. But there's one thing we've left out here, which is, remember the special thing we knew about the result of the natural recursion, which was that it was going to be sorted? So what we're going to do here is we're going to say assume LST is already sorted. Because we need to communicate that fact from sort images to whoever designs insert. Because if the person who designs insert doesn't know that, then what are they going to do? They're going to have to resort again, and they're never going to get anywhere, because they're going to come back to this same helper rule. But now we know that the list is sorted. So insert has a smaller job to do than sort images. All it has to do is put its first argument, img, in the right place in its already sorted second argument, lst. Let me go over this one more time, because there's two things that happen here. First, we set up some examples, quite ordinary, and we added another example partway through, also quite ordinary. The two main things that happen here are, one, we realized that the natural recursion was going to produce a sorted list, and that was going to be an important fact. It meant some of the work had really already been done. And we just made a note about that fact right here to ourselves so we wouldn't forget it. Then we realized that what ... needed to do was to put the first image in the right place in the sorted list. Then we invoked the operate on arbitrary size data rule, which says you must use a helper function to do that. And so we invented the name of a helper function, insert. And we made a wish list entry for that helper function. And there we go. And now we can run at this point. And we have a lot of failing tests. Okay, we have a lot of failing tests because sort kind of exists. Sort is done, but it's wishing for a function insert, and insert isn't done. We've got a stub for insert. But right now, at least, sort images looks done unless there's going to be some problem that crops up. Its tests are well formed, and it's wishing for our function insert. Turning back to our overview diagram, we started with arrange images, which we split into two functions because of the function composition rule. Then we went and finished layout images. Sort images is done, but while we were doing it, the operate on arbitrary size data rule caused us to wish for another function, insert. So now arrange images and sort images are both probably done, as long as it turns out that insert works properly and it turns out there were no mistakes in arrange images and sort images. So next we've got to focus on insert.